We are going to be talking about forces, Newton's laws of motions, translational equilibrium, free body diagrams, resolving vectors into components for tension, for example. And let's begin. Forces. They are a push or pull on any object. It causes that object to change its state of motion or lack of motion. It is a vector that is represented by an arrow. And I think we might have talked about this before, but a net force is just a resultant force, and it is a combination of all forces acting on an object. It is balanced or unbalanced. Forces can go in many directions. There can be multiple forces on an object, and we can predict how that object will move based on the forces that are acting on that object. There are different kinds. There is contact forces, such as friction, tension, normal, air resistance, applied, spring. There are also non-contact forces, such as gravitational, electrical, and magnetic. Newton's laws of motion was actually discovered by Galileo. Newton's first law. So you don't have to draw all this. This is just some introduction. So Galileo imagined a marble rolling in a very smooth bowl, simulating no friction. If you let go of the ball, it always rolls up the opposite side until it reaches its original height, and it actually comes from the conservation of energy. No matter how long the ball was, it always happened the same way, that the ball would reach the same height on the other side. Galileo imagined an infinitely long bowl where the ball never reaches the other side. So this brings us to Newton's first law of motion. It is the law of inertia. Objects are going to stay in motion, or they will stay at rest, unless they are acted on by an outside force. So, for example, the ball in the bowl would roll forever, supposedly, if there were no friction, no forces that were acting on it. Here are some examples of a rock staying still unless a force is acted on it that is greater than it sitting there. Here is an example also of inertia because the plates are sitting still, and you can actually do this where you pull the tablecloth, and if you do it in the right way, you can actually keep the plates in its place. Inertia. What is inertia? It is an object's tendency to resist change. So if you look at this guy down here, as he's driving, his body is moving forward. The car stops, but he is still moving forward. Another example is where this van down here has the ladder on the top. Because the car gets hit and runs into the truck, the ladder on the top continues to go. So an object is going to want to continue doing what it was doing. It's going to take force to stop the object from doing what it's currently doing. Translational equilibrium. It is when net force of an object is zero. It is also known as the state of steadiness. It applies to vector quantities. It is a balanced force, or balanced forces. So what this means, signified by sigma f, equaling 0, this means the sum of all forces equals 0. So when you have many forces acting on an object that equals 0, you have translational equilibrium. Here it is shown with an object that is experiencing 4 different forces of different quantities. However, when you add them up, it all equals 0. Over here also, 75 minus 75, 50, and 50 down. They are different from the vertical versus the horizontal. And then this is an example of translational equilibrium. Static equilibrium is also equilibrium, but it is for an object that is at rest. So the net force is 0. For example, a hockey puck on ice. It's just sitting there. There are 2 forces acting on it, but they do cancel each other out. These are balanced. Another example of a balanced force is support force. It is one of the forces that act against gravity. So here we have gravity pulling down on the book at 20 newtons. However, the table is also pushing up with 20 newtons, therefore allowing the book to stay in place. It also keeps the physics book from going into the ground. So this is a balanced force, and this is also known as support force. Dynamic equilibrium, in contrast to static equilibrium, is equilibrium that are for objects that are moving in a straight line, and therefore their net force is zero. So, for example, here is an airplane that is experiencing, it's flying, and it has thrust, which is going forward, propelling it forward. However, it is experiencing drag of the same quantity or the magnitude as its thrust. The up thrust is negating the challenge of the weight. So here we have a balanced force or balanced forces that are equaling a net force of zero. Another example of dynamic equilibrium, for example, if Mrs. Perez were pushing, so bicycling away with a certain force, there is an equal and opposite friction force. So therefore, if I'm keeping a constant velocity, I am experiencing dynamic equilibrium. Newton's second law. This actually concerns examples where there is a resultant force. So what does that mean? Newton's second law of motion states that acceleration is directly proportional to force and inversely proportional to its mass. This law shows how an object will react based on its mass and how much force is applied to it. How is force measured? It's measured by newtons. So force is its mass times its acceleration. And the units of measurement are kilograms, and then the acceleration we all know to be meters per second squared, and it can also be denoted as s to the negative 2. So 1 newton is equivalent to 1 kilogram meters per second squared. It is equal to the force to accelerate an object weighing 1 kilogram 1 meter per second each second. So what that means is that you can push it with 1 newton force, a mass of 1 kilogram, accelerating at a quantity of 1 meters per second squared. That is what 1 newton is. Here's an example. A 5 kilogram object has an acceleration of negative 4 meters per second squared. Find the net force that causes this motion. We know that force equals mass times acceleration. So all we need to do is plug in the items. So we have, and I forgot to put kilograms here, 5 kilograms times negative 4 meters per second squared, and that will give you newtons, negative 20. Here's another example. A 20 kilogram object accelerates from 5 meters per second to 30 meters per second in 15 seconds. What is the net force on the object? In this instance, we have the same equation, F equals ma. However, we're going to solve for a, and we know that actually acceleration equals the final minus the initial over time. So here we have our answer of 1.67 meters per second squared. Then we can find our force now that we have our acceleration. So that is our answer, 33.3 newtons. Newton's third law of motion. And you might have heard this before. For every action, there is an equal and opposite reaction. One thing to note is that in this, forces come in pairs. So that's why there's an opposite reaction for every reaction. If object A exerts a downward force on object B, then object B is going to exert the same force on A, but in the opposite direction. If you've never wondered why you're able to sit on your chair and not fall through your chair, you can thank this law. And it is from the normal force pushing back up on you. So for example, here it's showing that there is a force of gravity pulling the physics book. However, there is an equal and opposite reaction of the table pushing up against the book. therefore keeping the book in place without falling through the table. Here's another example of the hand, which is called body A, exerting force on the table. Body B, the table is going to exert its force back on the hand in the same magnitude as that of the exertion of the hand onto the table. Another thing that you need to learn is free body diagrams, and you've seen them, you just didn't know what they were called. So a free body diagram is just a drawing with vectors that shows all the forces acting on a body or object in all directions. In order to draw a free body diagram, you need to draw the body of interest. You need to draw all the forces that act on that body due to other bodies and forces. Make sure to label the vectors and show correct directions. If the values are given, you want to add the vectors, give the net force of the body, because this might help you in solving a specific problem if it comes to that. Here's an example. If you have a mass hanging on a rope, what forces are acting on this? So, in order to do this, you would draw a picture that looks like this. You would have the ball and two forces, one that is weight and one that is tension pulling up. String over a pulley. Where are the forces? To draw this, here are my bodies, and with the vectors labeled as, here mg means gravity, and gravity is down here also, and then T for tension. So it is pretty much the same, equal and opposing forces. To determine the amount of influence of a single vector, a force at an angle exerts both a vertical and horizontal component. So before when we were learning about vectors, we were learning how to find resultant. Now I'm asking you to find the force of the horizontal and the vertical component. So it's a little bit different. Instead of like a person is traveling at a certain angle, now there's a force pulling at a certain angle, find the x and the y components. So if you don't remember, you can refer back to the vectors and the scalars video, but pretty much what it's saying is that with this dog, if I am pulling him with a certain amount of force, we know that the dog is experiencing a vertical force and a horizontal force. And if we take these two forces and find the y component and the x component, we know that that is going to be equal to the resultant. Here is our dog, Fido, and we have our vector drawn, and we are given a magnitude of 60 newtons for the force that is being pulled on this dog. When we draw the x-axis, we know that this is a 40-degree angle. Given these two numbers, we should be able to figure this out, given that we already know how to calculate for each side of a triangle. So here I am given the sine of 40, and this is going to give me my force for my vertical, or my y-axis right here, over 60 newtons. When you solve for it, you should get 38.6 newtons for the force of the vertical vector. For my x-axis, I figure this to be 45.9 newtons. An 800 kilogram beam supported by two ropes. That is what we're looking at. So here is the first rope. The second rope is right here, each with a specific angle if you were to make a 90-degree angle. All holding up this beam right here, which is 800 kilograms. Well, let's go ahead and look at what we know. We know that nothing is moving, that the ropes are holding the object still. So given that we know that F equals ma, and that acceleration is 0 because nothing is moving, we know that the sum of all the forces will equal 0. That means our x components are going to equal 0 and our y components are going to equal 0. How do we do this? So step 1, you want to first draw a free body diagram of the picture. So this is the picture, but we're going to put this into a little bit more user-friendly mode. Here is our free body diagram. So notice that my body is a very tiny point where the vectors are coming from, showing the tension in rope 1 and rope 2, and then the mass, which is 800 kilograms of the beam. Now we do draw a horizontal line, the x-axis, in order to show that we understand that if you were to split this in half right here, that you would have a 90-degree angle. If we're given that this is 20 degrees and the second angle here is 30 degrees, we should be able to find that the angle over here closest to the x-axis for rope 1 is 70 degrees, and we have 60 degrees over here for the angle closest to the x-axis for rope 2. Step 2 is to break down each rope and the beam into x and y components. So what are those? Here's what it looks like. Here is the x and the y for our rope 1 and our x and our y for rope 2. We also do know that when we decide we want to take this 800 kilogram, we do need to transfer this into newtons in order to better work with it. How did I get that? We used the weight equals mass times gravity, and that will give us our weight in newtons. So this is the force of the 800 kilogram beam pulling on the two ropes. Step 3 is to list all the forces in the x and the y directions. So here we have our three objects of interest. We have rope 1, 2, and the beam. To figure out the x and the y components, you're just going to do your normal sine and cosines of whatever angle you are trying to figure out. So here we have 70 degrees. So for rope 1, for the x portion, we are going to have a negative T1 cosine of 70. And remember that cosine is just the adjacent over the hypotenuse, and then when you rearrange it, then you get this. And it is negative because it is in the second quadrant. It is going to the left. For your y portion, or your y component of your rope 1, that is T sub 1 sine of 70. Over here in your second rope, rope 2, you are going to have the sine and the cosine of 60. And for your beam, we actually don't have an x component, so that is going to be 0. And we have a y component of negative 7,848 newtons. And the reason why that is negative is because if you look over here in our free body diagram, the vector is going down. So therefore it is negative. We go ahead and now we remember that the net force, the sum of all forces, needs to equal 0 for both the x and the y components. So all we need to do is just add these up and add these up and set them to 0. We can go ahead and solve them. So cosine of 70, put that into your calculators, cosine of 60, add up these factors and set them to 0. So that would give us negative 0.342 T1 plus 0.5 T2 equals 0. And then let's go ahead and move this negative 0.342 over, and then we get 0.342 positive T1 equals 0.5 T2. This will come in handy later. For your y components, go ahead and add those up and set those to 0, and we get this final answer down here of 0.94 T1 plus 0.866 T2 equals 7,848 newtons, because we moved this over 1 onto the other side of the equal sign. Next, step 4 is to substitute one variable into the other equation. So we are going to substitute this into the other equation. But first, we need to go ahead and solve for T1. So we just get T1 by itself, and that equals 1.46 T2. We're going to take this and substitute it into our other equation over here. So all we need to do is put 1.46 T2 into this right here to supplement, or in order to substitute for T1. Here's what I have. And when you solve for this, you should get 1.37 T2 after multiplying, plus the same thing, the 0.866 T2 equals 7,848 newtons, and keep solving, and eventually you will get T2, the tension in rope 2, will be 3,297 newtons. Yay, now we have our variable. We have our number for T2, so now all you have to do is solve for rope 1 by plugging in this number back into this small little equation up there. So we have T equals 1.46 T2, and we have our T2 as being 3,297 newtons. Plug that in, multiply, and solve. And that is your answer. So now you know that your tension in your rope is 3,297 for your second rope, and your other tension in your first rope is 4,813. All right, so may the forces be with you, and good luck, and we'll see you in class next.